In this video, I want to describe to you three examples of where advanced packaging is already in use in your iPhone or your iPad. So I want to give you three sample cases. Two of them are where this advanced packaging is used for form factor reduction. That is to reduce the area that these chips occupy on your PCB. And I'll also give you one example in the case of the image sensor for the camera for your iPhone or your iPad, where this advanced packaging helps in improving the performance or improving the image quality of your camera. So the very first place where you can observe this advanced packaging technology being used in your smartphone is the microprocessor. So if you open up this A5 microprocessor chip and look at it sideways, this is how it looks. So this is how it looks. So what you see if you look at this side view is that you can observe three pieces of silicon in here. One is this A5 microprocessors, and then there are these two chips on top of it, which are essentially two DRAM chips, which are stacked on top of each other. And this microprocessor is in one package. So this is one package, and these two DRAM chips are in this another package. And what you have is essentially this stacked DRAM packaged on top of this A5 microprocessor. So this is also known as a package on package implementation, or where you have, or also acronymed as POP. And what again you can observe these set of solder balls. So this is a flip chip ball grid array. So you can see this array of solder balls which are connecting this microprocessors to the PCB below. And you also see these another set of solder balls which are connecting this second package, this second DRAM package to carry the supply voltage, and also connecting this microprocessor to this DRAM. So this is another cartoon which is depicting the same. So you have this first package of, so you have these two packages. One is your microprocessor, and then the other one is the stacked DRAM, and then this microprocessor is connected to the PCB below using this flip chip package. So there are these micro bumps, and then there are these ball grid array which connect this A5 microprocessor. And then there are also these second set of solder balls which are taking the supply voltage from the PCB below to this DRAM chip. And so this package on package implementation, it's mostly for a form factor reduction, where essentially you in your iPhone or your iPad or your smartphone, where you're constrained for space, by stacking these packages on top of each other, you essentially achieve a form factor reduction. So I want to quiz you on in this package on package implementation, which package should be on the top. So there could be two possible implementations. One is, let's label one as implementation A, where the DRAM chip is on the top of the microprocessor, and the option B, where the microprocessor is on top of the DRAM. So I want to think, to guide your thoughts, I want you to think along two directions. One is that which one is better from a heat management perspective, which option, either option A or B, is better from a heat management perspective. The other thing I wanted you to think about is which option is better from an IO perspective, which option is better to manage the input and output signals coming into this package. From a heat perspective, most of the heat in this package is generated in this microprocessor. So you'll have most of your heat being generated here. So from a heat management perspective, it looks like option B might be a better choice, because in that case you can put a heat sink here and you can have the steel plate as a heat sink, and you can better take out the heat from this package. On the other hand, in option A, you'll have this microprocessor heating up, and that in turn will heat up your DRAM. So if your DRAM chips heats up, then it decreases the retention time of your DRAM cell, and you need to refresh it more often. So it's bad so heating up of this DRAM chip is bad. So from a heat management perspective, it looks like option B might be a better choice, which places the microprocessor on the top. Let's look at it more from an I/O perspective. So from an I/O perspective, if you think about these two packages, if you have option A, it's better from an I/O perspective, because most of your I/Os are actually coming to your microprocessor, because your microprocessor needs to communicate with your NAND flash, with your gyroscope, with your accelerometer. So if you have this microprocessor on the bottom, you could actually use this this microprocessor and use this flip chip package to get your I/O signals into your microprocessor. On the other hand, if you had a microprocessor on the top, you'll need these wire bonds to bring all these signals from your PCB to your microprocessor. So you'll need a whole mesh of wire bonds to connect all the I/O signals to your microprocessor. So from I/O perspective, option B is bad. So from an I/O perspective, option A is the winner. And as we saw in the current implementation, which is used commercially, we have this DRAM on top of the microprocessor. So probably it's being driven by this I/O perspective. So second scenario where this advanced packaging is used in your smartphone is in this NAND flash memory chip. Again, advanced packaging in this case is used for form factor reduction. So if you pry open this NAND flash chip and package, and then look at the different IC chips, so you see this stack of these ICs on top of each other. In this case, I'm showing you a stack of 24 chips, NAND flash chips stacked on top of each other, and each of them has a capacity of 4 gigabytes. So this stack has an enormous amount of storage capacity of 96 gigabytes in this one single package. And you can see these chips are stacked in this domino fashion. So you have these one domino of these chips, and then you have another domino on top of that, and then they are connected using these wire bonds. And looking at these wire bonds, it's almost incredible that these chips, the stack is functioning without these wire bonds shorting into each other. Right, so this is another picture. So this is showing it from another angle, where you have these stack of these NAND flash memory chips. There's also a controller chip which is on the top. So this controller chip needs to communicate with so looking at this, it's almost looks like as if Spider-Man visited here, and you have these incredible wire bonds, and none of them are shorting with each other, and it's just amazing to see that this package still works. And there's been a tremendous amount of advancement in the wire bond technology as well. Traditionally, these wire bonds used to be made of gold, but with the gold prices going up, they're actually nowadays they're actually made of copper. and but there's still a lot of inertia left in this wire bond technology, and it's pretty prevalent in use commercially at the moment.